Hi everyone, Ms. Magar here. We're going to be going over a pulley system problem for physics. So what we're going to do is we have a slightly different example than what we did in class today with just different numbers. Essentially, we're going to have two masses on different inclines. One plane will have friction, the other one will not. And what we're going to do is we're going to calculate the acceleration of the system and also find the tension in the ropes connecting the two masses together. Okay, so this is the note from earlier today. Very similar setup. What you are going to notice though is that I swapped the masses around. So in this case here, mass number 1 is going to be 22 kilograms, and it is sitting on an incline of 36 degrees in the system. Mass number 2 is going to have, which is 12 kilograms. It is on the other side with an incline of 20 degrees. One thing to note though, you have a coefficient of kinetic friction between mass 1 and the ramp itself. Mass 2 and the ramp is frictionless. So the first thing I really want to do is draw a free body diagram of my system. I want to look at all the forces acting on each of the masses individually, and then we can approach that to find out what our acceleration is going to be, because again, your two masses are connected. The rope between them is going to be taut, so they're going to move as one. So the acceleration of the system is literally the same. Mass 1 will have the same acceleration as mass number 2. So I want to break this down into components to make things easier for me here. So what I'm going to do is I want to draw all of the components in the x direction and the y direction that are acting on each mass. Now, because you have an angle here, we have to break them down into their components. So for mass number 1, I'm just going to look to the original drawing here. This is my force of gravity acting on mass 1. Now I drew it in purple because it is a vector, so we're going to have a y component to that and an x component to that as well. So my y component of my gravity is pointing like this. I'm going to put that on my free body diagram. So here's my FG, and here's my FN, or my normal force pointing up. Now, just a friendly reminder, because it's acting on an angle, your FN and your FG aren't going to be the same value, face value. We need the y components to add up to give us that purple vector value. So having said that, my FG is going to be my mass 1 times gravity, and that's cosine 36.0 degrees. Now again, I have an x component to that as well. So here's my x. Now this one is going to be m1g sine 36 degrees. Now, if you remember, we got the sines and cosines based off of SOHCAHTOA. So the angle, again, that I'm dealing with is the 36. That's going to be the same value as this angle right here. All right, I have my normal force up. I've got my force of gravity pointing down. That's my m1g cosine 36. I've got my x component of that gravitational part. And now my system is going to be moving down and towards the left. So I'm just going to remind myself here that my motion is happening in this direction. We'll say towards the left. I also have tension in the rope pulling back. So this is going to be my FT. And I also have friction. So remember, friction is going to oppose your motion. So that means my force of friction, I'll make that here, that's my FF. Now, because we have an angle and the object is sitting on a slant, force of friction, just a friendly reminder, is made up of mu times my normal. And remember, my normal isn't just mg. My normal component has to be oppositional to my force of gravity pointing down. So that means when I put my force of friction in, it's going to be, so there's my mu k value, m1g cosine 36.0 degrees. So that's my 22 kilogram mass. Just gonna move my 12 over here for a bit more space. Again, we have a normal force pointing up. We have our gravitational component. Here's my FG. And remember, this is going to be M2G. This is cosine 20 degrees. And then my X component to that, again, it's sliding like this. Gravity's going to want to take it down in this direction here. So that means I'm going to have an FG to the right, and that's going to be M2G sine 20 degrees. Okay, I think I've got everything all mapped out. Now, we have to remind ourselves, which direction is this is accelerating in? So remember, we're swinging the two masses that are pitched like this to be in one plane, which means my motion is going to be happening in the horizontal direction, or left and right. So that's my blue vectors that I'm concerned with. So my F net is going to be my total mass of the system times the acceleration of the system. But we also have to consider all of the little blue arrows here going left and right, adding up to give us our total F net in the X direction. So this means I'm going to be adding my components here. Oops, I did forget one. Sorry. I also have a tension force on mass number 2. So one reason why I'm not including it in my algebra right now is because the tension is going to be the same. It's just going to be, so same magnitude, just opposite in direction. So the tension for mass number 1 is going to be pulling this way. The tension for mass number 2 is pulling this way. So they're, again, exact same magnitude, opposite in direction. So they're going to add up to 0. So we don't need to include them in our calculations. So go back to F net X. So my total mass times my acceleration is going to be my M1G sine 36 degrees. That is moving towards the left, plus my force, my force of friction component here, which is my mu K M1G cosine 36 degrees. That's moving towards the right. And then we have one more that's on my M2. So that is M2G sine 20 degrees, and that is also moving towards the right. So we need to make sure that we have the same vector directions. We have lefts and we have rights. So we want everything, again, is moving towards the left. In order for me to do that, I need to change my rights to negative lefts. So I'm going to change this, and I'm going to change this right and the sign at the front as well. So now I'm going to plug in all my information, and we're going to find out what our acceleration of the system is. So we've got 22 kilos, 9.8 sine 36.0 degrees. That's to the left. So now we're subtracting my mu value. So 0.16 times mass number 1, that's 22.0, times my 9.8 cosine 36 degrees. That's also moving now towards the left. And then we're going to subtract the other component off of that. And that's going to be 12.0 times 9.8 sine 20.0 degrees, and that's moving towards the left. So when I add everything all up and I crunch my numbers, I'm going to get 58.597 newtons towards the left. I want to get acceleration, so I have to divide everything by my total mass, because again, this system is traveling as one. So acceleration of my system is going to be 58.597 newtons towards the left. going to divide that by my total mass. So that's going to be 22 plus my 12 kilos. All right, I'm going to get 1.7234 meters per second squared, and that is going towards the left. Now, significant figure-wise, I'm keeping 2 sig figs. So my acceleration is going to be 1.7 meters per second squared to the left. For part B, we're looking for the tension between the ropes. Again, the system is traveling as one, so the tension from the one rope is going to be equivalent to the tension from the other side of the rope. Opposite in direction, but equal in magnitude. So there is an easy way to do this and a hard way to do this. Now, when we go back up here and just look at our free body diagrams, if you're trying to find tension, you want to pick the one with the least number of vector arrows coming off it in that particular plane. So if I look at my first mass, the 22 kilogram mass, I have a force of friction, I have a tension force, and then I have a gravitational component to it. So I have 3. Whereas my smaller mass, the 12 kilogram mass, I have tension, and then I've got its oppositional force of the force of gravity pulling it downwards. So the easier one in this option here is going to be mass number 2. So I'm going to look at my forces here, again, acting on mass number 2. Just draw a very quick free body diagram about this one here. So here's my 12 kilogram mass. I've got my X component, my force of gravity. This is going to be M2 times G sine theta. And then I've got my tension force pulling back. So my F net in the X direction here is going to be mass 2 times acceleration. And that's going to be equivalent to my tension force plus my M2G sine theta, and that's going towards the right. So from the previous question, my acceleration is happening to the left, totally fine. We're going to use mass number 2 because, again, when we talk about tension, even though the system is traveling as one, your tension is going to be determined based off of the individual masses themselves. So mass number 2, we've got, I'm just going to rearrange my equation here. My tension force is going to be equal to mass 2 times my acceleration. That's going towards the left. Sorry, minus my M2G sine theta to the right. Now, like I said before, you have to have the same directions in your vectors. So we're going to change a right to a left. So for this, I'm going to plug my numbers in and we're going to evaluate. So my mass 2 is 12.0 kilos. My acceleration, I'm going to use 1.7234. And that's towards the left. Plus my M2, so that's going to be 12.0, 9.8, sine 20 degrees. And that is also going towards the left. All right, when I crunch my numbers, I'm going to get 60.9023. This is newtons going towards the left. So my tension in this case here, again, we are keeping two significant figures. So it's going to be 61 newtons towards the left. So if you wanted to use mass number 1, just draw a really quick free body diagram about this one. So just a friendly reminder, we've got a mu k value of 0.16. The mass is 22.0 kilos. And again, we're talking about the tension force here. So we've got my gravitational component in the x direction, again, pulling the mass down. We've got our tension, and we also have our force of friction. And remember, your force of friction is always opposing the actual motion itself. So because it's going down, my force of friction is going to be going, we'll say, towards the right in this case. So my F net, again, which way is my system moving? It's moving towards the left. So I've got my M1 times A, that's going towards the left. Now this is the sum of all my forces acting on my mass. So I've got my Fg plus my Ft plus my Ff. So I want to get my tension force, isolated here. So I've got my M1 times A to the left. From that, I'm going to take my Fg off of it. And again, my Fg is going towards the left. And I'm also going to take my force of friction off, but force of friction is moving towards the right. So let's plug in all our information here. So we're going to plug our information in. So my mass, pardon me, is 22 kilos. My acceleration of my system, 1.7234 meters per second squared. That's going towards the left. We're going to take my force of gravity off of that. And my force of gravity, remember, isn't just straight down. We have the x component to it. So it is going to be 22.0 times 9.8 sine 36 degrees. And that's going towards the left. And then we're taking off my force of friction. Again, has an x component to it. So that is my mu k m1g cosine theta towards the right. So when I plug this in, it's going to be 0.16 times 22.0 times my 9.8 cosine 36.0 degrees. And again, that is going to the right. So when I plug everything in, I need to change my right to a left. So I'm going to do that. And you're going to get a tension force, in this case here, negative 60.9038 newtons. And that's going towards the left. And in physics, we don't like negative magnitudes, so we're going to change that to positive, which means our direction has to switch. And we are keeping 2 sig figs, and you're going to have 61 newtons towards the right. So either way you solve it, you're going to get the same answer. Try to pick the one with the less vector arrows acting on the object itself. It'll make your life a lot easier. I hope that was helpful. If you have any questions, send me an email, and good luck on your test.